All right, so this is building query for November 6th, 2020. B5, do you want to just take it away?
Yeah, totally. So today, I think we're going to be having a fairly early discussion on some of the actual on-the-ground implementation of the or definition of requirements for the identity and access control system that we are currently missing. And so hopefully this is going to be a chance to mainly just sort of air out some of the thinking and some of the concepts. And this is sort of building on a bunch of work we've been doing on logbook and specifically what logbook is and isn't going to do. And so today what I want to do is just walk through an example story that I think defines a couple of key things that we need to have figured out correctly in our heads to understand how to properly design, how to modify a few existing sort of like things a query does, namely syncing up of stuff, and then how to design a new thing, which is the storage of some data structure that defines access control and what does and does not constitute both a collaborator in a data set and a data that is to be considered part of a data set. So it's kind of a bit of an exploratory discussion, but I've prepped a very cursory doc to sort of walk through and talk through, and hopefully that'll serve as a good sort of jump off point for questions that others may have. Before we get started, that's kind of a all over the place introduction. Does anybody have any questions that they'd like to see openly answered about identity or collaboration, or do we want to just go into the example first?
I don't know, I guess the use case top of mind is the ability to like save as the same identity from different places, which I'm sure we'll cover, but just want to put it out there as a thing that is needed.
Perfect. That's an ideal tee up. Thank you, Chris, because I think that's exactly what we want to cover. That's
definitely a use case that we are planning on having in the focus of what this is targeting.
Totally. And I think that some of this is going to have to be like walking through things that aren't properly defined at all in spec yet, but that is the goal that we're talking through. And so this example actually speaks directly to that, and we'll use that example as the sort of like introductory point. Cool. All right, I'm going to share a screen, and I'll just quickly talk through this thing, and I'm going to blather on for a bit at the beginning just to set this up a little bit because I haven't done the proper writing of the text of this yet. But cool. Let's see. Does that? Hopefully everyone sees the query.io new specs site. Is that legible at all? People see this? Cool. All right, so what this is going to be is like a quick sort of run of show for a simple collaboration that exactly talks about kind of what you were describing, Chris. How do we have multiple key pairs and possibly a single profile, but in this case, multiple profiles, collaborating on the same data set? And so before we get into the actual script, there are 8 steps to this that I believe constitute the minimum set of steps that properly describe and capture some of the complexity of the project or of the design requirements of an identity system, and specifically a delegation system. And all of this is sort of guised under collaboration. But I think what we're going to talk about today is like the sets of data structures that are involved in that process, and sort of lay those out on the table. But just to sort of give a high level view of what's going on here first, just so everyone has like a pretty basic, so we have like a starting point for this discussion. These are kind of like user A running and user B and a user C. So there are 3 users collaborating in this. Users are to be thought of as, in this case, for this purpose of this discussion, people sitting at computers. And they're running commands. So this would be user A running query setup. And then user B running query save to user A. So for a quick run of show of what happens, query A creates a brand new profile out of thin air, does nothing, nothing special. It'll create some data structures, which we'll get into in a second. User A then saves a brand new data set called DS1. They then run query connect for reasons we'll get into in a second, which basically is just to sort of acquire some knowledge of other actors in the network. Then they create a new thing using our access RFC that we've talked about in the past, and it's in our RFC's repo, to provision a access token, which is in step 4, we're actually giving permission for another user, user B, to do stuff to data set DS1. This is not properly recorded. I should say allow write B to dataset DS, my dataset DS1, or user A's dataset DS1. Then user A pushes to user B, sending that dataset to user B. Then user B, this is the new thing, user B, they're the new and interesting thing, I should say. User B then saves to user A's dataset, which is something that we can't do right now, and is kind of the whole point of this discussion, right? The capacity for somebody else or myself somewhere else to be able to add something new. And then the last 2 steps sort of like are rounding out our knowledge of how should this work. User A then pulls from user B, who has made a change, and so they will actually see something new when that happens. And then finally, a completely separate user C pulls from user B that same data set initially created by A. So it's a little bit, we're in a bit of like a dots and lines mentally scenario. But there are a number of data structures that are affected by this, but what we want to end at the end of this story, user A has created something. User A has added user B as a collaborator. User B has modified that thing that user A initially made. And user C is able to see both of the things that users A and B have done and understands that to be a single canonical history. So they're not seeing branches, they're just seeing, they are cognitively just thinking about data set created under user A / DS1. And yeah, so what user C sees at the very end of this is actually the commit created by user B and the history of user A's first commit and user B's second commit merged into a single time log. Does everyone follow so far? Cool. Okay. Complicated. So to do this right, we have to go through a couple of key data structures that are involved here and sort of talk about how they all interplay. And so I've created 3 columns here: data structures created, data structures modified, and data structures moved at each step. And so the goal here is just to talk through, hey, we're making something, what are we making, what are we modifying, and what are we moving in each step of this process. And so the best place, and before we get into what happens at each step, it's best to just talk about what each data structure is. I've only gone so far as to properly make like a pretty diagram for keys, which is a definition of a public key and a private key. But to go through the list, we have keys, we have profiles, we have 3 flavors of logs, which we'll talk about because that may not necessarily need to exist. And we have access tokens. So those are generally 5 distinct things. To start with, Dustin.
An important thing missing here is also the history ID for the data set, formerly known as init ID in a lot of the code. But it'll be the stable identifier that represents data set history that will not be modified by things like renames or transfers between users, things like that. Absolutely.
That's a really good point. We should talk about how I have not actually, in this script, I've kind of simplified and removed the notion of identifiers entirely.
Sure. It's an interesting piece of info just because it's kind of analogous to the IPFS hash, which is an important detail shown. It's not changing which the IPFS hash, well, it doesn't change, but the IPFS hash gets replaced when a new version exists. Totally. I just wanted to point it out, that's all.
It's a really good point. So like in these examples where I have dataset log A and branch log A, you'll see here in this step, branch log A is actually modified. So we do need a consistent way of referring to both branch log A and dataset log A. And that's wildly important for any of this to work at all. Which we can, I honestly think that like references and identifiers should be a sort of today I want to focus on the orchestration side of things and specifically the delegation part of things, because I think it'll help us understand how logbook, which is a sort of state coordination mechanism, and this new identity and access token system is going to have to behave to complement that. Great. So yes, it's a really good point. All of these have identifiers generally. Some of them have the identifier literally baked into the name. So that we have hash 1 the identifier is right there. In these ones, we'll actually have to like, the identifier will be part of the data structure itself. So getting back to the enumeration of types of data structures we have technically we have public key and private key, but for the way you sort of should think about it cognitively is just a key pair, which is like both a combination of public and private. So we have a key pair, which is each user is going to have one. So there's a key pair for A, there's a key pair for B, and there's a key pair for C. There is a profile, which is distinct from a key pair. A profile is a thing that a user is basically going to state that's going to contain, that is a data structure that describes who that user is. So, and that's a change that we're making to the spec is we're no longer saying that that is going to be universally unique and coordinated by the registry. So it is possible to have two users named dustmop. And the way we will disambiguate dustmop is through identifiers, which I'm going to push to being a separate discussion for now. But it should know that basically in step one, when I run query setup, I get a lot of things right out the gates. I get both a key pair and a definition of a profile, which gives me a username that I can share with other people. And I get this profile log, which is a description of changes to my log of my profile over time, and will be a place where I will eventually do stuff like key rotation. Again, I don't think we're going to get wildly into it today. Just the profile log is going to be an append-only log. And so each of these things, the three flavors of logs that we're talking about, profile, branch, and data set, sorry, in the proper order, the profile, data set, and branch, are all append-only logs that have a single author, if that makes sense so far. And everyone follow with that? Cool. The last new thing is this notion of an access token. For our purposes, we are heavily considering this to be something called a UCAN, which is a thing that an access token, a UCAN for us is, or an access token is going to be a data structure that is signed with the private key of the person issuing, but it is going to be always targeted at a person. So that's why I've named this access token A to B. And so it is an explicit thing and a verifiable data structure that delegates some capability described inside of the data structure itself from user A to user B. And to be even more specific, from key pair A to key pair B. So access token A to B takes the public key of B and uses that as the basis for creating the token. And so that's one of the newest things that we have, and is going to be the sort of biggest lift and load that the identity system and delegation system, collaboration subsystem that we're going to have to design will have to hang on to. So that's the new stuff. Let's walk through the script with what moves and what changes. So just talking through this in terms of data structures, I run setup, that makes some stuff. Then I run save, which does this, and this is all exists right now. As soon as I run save, the first time I create a dataset log, which contains the name of the dataset and who made it. And then inside of that is actually a branch log, which is where the commit itself lives. So the branch log is the description of, hey, this is how this is where #1 was created. And when I type query log, what I'm really looking at is the branch log as it is right now. That's going to get more complicated in a second. In this query connect step, this needs to be part of this conversation, but is actually quite fluid in practice. What needs to happen is node A needs to acquire knowledge of B's public key somehow. This could be, B could be pushing something to you, and then that could actually move the public key of B to a place. But in this example, I'm just saying, I'm going to run query connect, and it so happens that those two nodes are online, and I acquire knowledge of public key B. And the reason I use that example is because there is a high degree of overlap with the current definition of peers, of the peers subsystem, and this new identity management subsystem. Right now, we have a thing inside of query that when you come into contact with other query peers, we write down a join of your profile information and your public key that is associated with that. That system actually, I think, is the best current foundation for a lot of this work. We have a new peer-to-peer based profile exchange service, which could be a really great, which plugs directly into all of this and is already populating and hydrating that system. And so I think that it's safe to say that using that as the foundation for this entire conversation is how this will work in practice, and then modifying it towards this defining a subsystem that can sort of interoperate with it for access tokens is probably the next important step. Because in this next step, in step 4, we now have somewhere locally a record of this public key, and we utilize that to make this command actually work. And so when I type query access allow write B, and I missed a piece here. I should have said B for A/DS1. I'm going to use this key, and I'm going to write is the thing that I'm delegating. So I'm saying, hey, I'm going to give write access to this thing, to this user, and that will generate this token, which embeds both their public key and my public key, and creates this new thing. So we have to coordinate those somehow, which is why in step 5, the biggest change from now, the way query works right now, to the way query will need to work to make this properly function, is when I do a push, I now need to piggyback. We probably want to piggyback on top of that the transmission of relevant access tokens, right? So, hey, I'm going to push data sets to you. Query in this example, peer B is set up as a remote, so I can push to them. I'm going to actually modify branch A in this before I even send branch A to include the information that I pushed. This is the way the query currently works. Basically, every time we push, we say, hey, I pushed to here, hey, I pushed to there. It's kind of not really relevant to the access conversation, but it's worth just noting for formality's sake. But what ends up on node B is the actual data, so the version information, the log that describes it. And this is actually incorrect. This should include not just the branch log, but also the data set log A needs to move here. I should change that, but I'm not going to waste your time. Assume there's another thing in this list. And at the same time, if we push the access token and say, hey, node B should be configured to say, hey, I'll accept any access token of which I am the subject. And so if you want to send me stuff that gives me new superpowers, I will gladly accept those things. And there may be semantics about what tokens are accepted in stores. And we need to be careful about that, because if we just say any user will accept any access token, that becomes a security problem where I can fill up your hard drive by sending you thousands upon thousands of access tokens. On B, I can use this new access token to do stuff. And in step 6, I create I run query save, and this time I make the target of that to be DS1. Under the hood, query is going to use validation logic to say, hey, you're trying to save from A to B, so we better have some token present to allow that to happen. That's purely a user interface perspective. Basically, that's not the actual security guarantee of all of this, which we'll get into in a second. But we do have all the ingredients we need at this step to say, hey, does B have the right to save to dataset A/DS1? When they do save, I'm going to create 2 new things. I'm going to create hash2, which will be the actual data representing the new version of the dataset. And I'm going to create a new branch log. And branch log B will be a new append-only log that contains my information about my contributions to dataset A/DS1. By my, in this case, I've just become B overnight. I see B's and I just think of myself. I wonder why. That's where, and what happens now, where this creates a new demand for logbook, or a new mechanism we are going to need, is some mechanism for automatically merging branch log A and branch log B into a unified history. And so under the hood, query has branches, but as a design goal, we don't want query to have branches, right? We don't want query to actually show these are all of A's changes and these are all of B's changes as separate things. We want to understand them as a single track, thinking of it as a single document. And so that, I'm assuming we are going to use something resembling a last writer wins auto merge type strategy, basically stealing from the world of CRDTs. I think it's actually a lot simpler in practice than it sounds in theory. But yeah, so there will be some mechanism for combining any number of collaborators and branches into a single branch. And there will also need to be a new mechanism for caching the results of that, because it'll probably be relatively expensive to calculate. Or at least it would be much snappier if we just calculated histories one time and cached them and knew how to invalidate them when we got new information. And I want to stop there for one last bit. This is where the security part comes in. The decision on what to include in the list to merge has to be dictated by this external system that carries access tokens. And so there's this funny seam where, in my head, the way it should work right now is the definition of how to combine any set of branch logs should be contained within logbook. It should be logbook's capacity to give you a unified history of any two branches. The decision of which branches to use should be the authentication subsystem's job. And it should basically say, hey, I would like, a user is now asking me for the definitive history of dataset A/DS1. And I currently don't have it in a cache, so I have to go calculate it from all of the logbook data that I have presently. And so I'm first gonna go ask the identity or the authentication subsystem and say, hey, which users, which public keys are collaborating in this data set? And then I'm gonna go, I need some mechanism to extract from logbook all of the branches that are authored by those keys. And then run all of those through the magical merge machine and come out with a canonical history. As a note, the question that naturally arises at this point often is, how do I eject somebody from that history? Basically, I gave B permission to do stuff and I no longer want to give permission to B to do stuff. And this is where I would write into either the dataset log or the owner of the dataset's branch log, that something called a tombstone, which says, I am nullifying I'm revoking the rights of access token A to B. And so when that operation syncs with other people, and that subsystem then says, hey, I want to know which branches I can use, we need to basically know that we should delete access token A to B or not use access token A to B because logbook contains the information that says, hey, I need to reject this. That part, the recording of tombstoning of keys inside of logbook, is admittedly kind of gross. But there is no existing decent, reliable research or writing in academia that I've been able to find that has a better answer for the key revocation problem, other than to use some commonly understood source of state for tracking where we should get rid of stuff. So that's a big open question for discussion, because it creates a really tight coupling between the logbook information and the identity information. And for me, I personally hate it, but it's probably just got to be the case. And I think it really speaks to some of the stuff that Dustin has been saying, where logbook should really should be a little bit stupid about the information it's recording. It shouldn't actually shouldn't be doing a ton of stuff. It should basically just record the operations and state transforms. Dustin, stop me if I'm sticking words in your mouth that you don't like.
More or less. I think it should be a store and synchronization tool, and other things observe it in order to make decisions like that. Yeah.
Okay.
The revocation problem is still hard. I don't really know what to think yet. But yeah, I think you've identified a good open question.
Azra?
Yeah. When you say storing identity in logbook, that doesn't mean like what we previously discussed like a month ago or so, that we're going to carry the profile info like user land info. This is just profile, like public private.
Just keys. Yeah,
okay,
just keys.
Okay, that works. I'm fine with that.
Absolutely no profile information inside of logbook itself.
Keys and IDs.
Yeah, with the exception of, this is a point of contention, but with the exception of the username. And I think when your username shifts, that should be recorded at your profile log.
I'm fine if that lands as an operation on logbook, but not as an identifier on logbook.
Deep agree. That's exactly how we see it.
I have a suggested hybrid approach, but that's, I think, out of scope.
Awesome. I would love to hear about that if we have time. Because yeah, actually to finish this out, and this is a perfect, I'm glad we're transitioning to the discussion, because that's kind of where this stops. To speak directly to the store profile information, we currently have a peer store and we have a profile exchange, both in P2P and HTTP implementations. And I think we should just keep doing that. And logbook and access token work should all be through these identifiers. We should not be using them for anything other than that. And so that kind of concludes it. When C pulls, oh yes, the last things to note is on step 8, the thing that is interesting or of note here is using our current definition of only pull latest version. When C does query pull from remote B actually has to calculate the merged history of what it knows to produce the result of what is the latest version that you're going to send or going to give to, actually no, that calculation happens on C. So when query pull happens, it's a 2-step process. The first one is a log sync. It sounds like it's going to become a 3-step process where it's a log sync, a token sync, and a log sync and any number of necessary token sync. And then finally a node C will decide what versions it want to pulls. By default, everybody only pulls the latest version. And so it will run the calculation locally of the merge calculation locally using the information that was just literally delivered from A and B and find out that, hey, hash 2 is the latest version and it only gets hash 2. And I think that's what's worth pointing out here is this setup robustly handles the problem of desynchronization as it kind of sounds between different peers, right? And so the upside of using our append-only log merge strategy stuff is this set of steps is consistent with the axiom that so long as everybody has seen the same messages, they get the same result. So if C were to try and pull from A before A had done step 7, where they pull from B, they would actually get IPFS hash 1, branch log A, and access token, and they wouldn't maybe get access token B. That would be a spec implementation question. They probably should. And if by some other external mechanism, node C ended up with node B's branch log and the access token, all of that is commutes properly. And so basically you can acquire this information from disparate sources and in disparate ways, and you will end up, as long as you get the same messages, you get the same results, which is another way of saying eventual consistency. We are not in the step between 6 and 7, nodes B and A are in disparate states, where B actually has knowledge of a commit that A does not have knowledge of, which is the way that Git works right now. This is why we have to type query or git pull to get the latest. And that's fine. The system is totally cool with that. And it doesn't hurt anything. It's not a bad or erroneous state. It's simply the case that you haven't been on the network recently. I think that covers all the points I wanted to cover. Asmir.
Couple hypotheticals. So given like literally what you explained right now, technically it should be possible that we have a remote D added to this mix, and let's say C pulled from A, and then they can push their own to D. Yep. They technically have their own fork, which can have a different history as long as there's an access token for
yes,
either C or D. And then we only have the issue of merging them back.
Yeah.
We talked a while ago about the magic merge machine in this case. And we kind of landed on like promote a branch to master. Is that what you explained earlier in terms of like resolving conflicts in terms of like who's the latest, or like somebody has to approve or pick?
No, you actually do have to merge the different branches. You can't have promote a branch to master because you don't evade the problem of a single history that includes commits from both peer A and peer B.
Yes.
Right, and so we need to actually fabricate we compute, pardon me, not fabricate, we're not making something up here. We need to compute from a set of branch logs, a canonicalized branch log or a authoritative branch log.
But in that scenario, how does like the canonical source of A in this case decide he wants to omit C but keep B commits?
Which is exactly
this. It's more a UI thingy right now, I think.
But at the technical level, the decision of what constitutes set membership or collaborator membership is the access tokens.
Yeah.
And so if there is no access token for C explicitly moving somebody in, then you don't include it in the merge operation.
Yep. This is a whitelist only kind of, and you expect that user to be a contributor and a writer, and you respect their rights in that case. Like you don't have rogue people writing.
Yeah. Well, but I think that's really interesting, right? Because rogue people can write. You can write forks, and it's actually
but you won't merge them back in that case.
Exactly, and it's entirely possible, which is just kind of bonkers to me, that my fork could be merged through the minting of an access token, right? Like I could literally just say, create an access token. A could create an access token for C, and then instantly, if the log data is present and you rerun the calculation, you now have retroactively merged all of C's commits into the history.
Is that our path to PRs?
I think so. Yeah.
Cool. Okay, good.
Dustin?
2 questions. First, step 4.
Yep.
When you say allow write, are you talking about B, the profile, or B's key pair?
B, the public key specifically. And that's, so I'm allowing public key B to write, not B, the profile information, not B, the username.
So if B rotates their key, they have to re-get added?
Yes.
Okay.
And so,
but this is where also committed to the history. Like if they had the old, like the access token, they could write their own new public key back into the log and move on.
They can rotate their keys. I don't think, so the access token, it will be very important to define the semantics of what operations are being granted by, so in this example, we have query access allow write, and write is a business logic definition, right? We get to define what write allows and doesn't allow.
Are you saying there might be a token for like allow key rotation?
Yeah, or allow admin, right? Like who can change the name of the data set? Who can add more collaborators to a data set? I could create a key that says this key can create new keys. And
we could use a similar mechanic to
a token.
Pardon
me, well, and that's actually so that's how the automation side of this works in my eyes, Asmir, and it's a perfect segue of like, we can use the registry. We can set up a system where users are really encouraged to create an access token that delegates to the registry the capacity to mint more access tokens. The reason that you would want that in an automation setup is we can use an OAuth strategy to have something running in CI, something running in a some other universe where they just create a key out of nowhere. But what that thing has locally is a set of OAuth credentials to get an access token that pulls that new key into set membership. So now you can say basically, and the reason that we want that on the registry is the thing that is promising to be online all the time, right? So you don't have this problem of, I have to wait until there's a synchronization point between A or B, right? The registry is the thing that is ideally has very high availability. And so I can use OAuth as a mechanism to request the generation of access token registry to robot. and that will allow us to create these really nice one-off patterns.
Technical. Oh, go ahead, Dustin.
So for that decision on the access token being about the key and not the profile ID, or the profile, sorry, is there an advantage to doing it that way, to doing it with just the key pair, as opposed to some ID that then has to be proven to have a key pair?
I think the cryptographic primitives of it are really important. The statements need to be tied back to cryptography to make them valid. I need to be able to use the public key to check the authority of the signing of anything. And so if we introduce a level of indirection where, say, that profile identifier refers to a log history that refers to a key, we ultimately have to go fetch that key.
I agree. There has to be something. There has to be some sort of what's the word I'm looking for? What's that word? Something that proves that someone has rights to it or whatever, like some sort of cryptography proof to it.
Proof, yeah.
Yeah, yeah, there has to be something, but I'm thinking more as a matter of like just the use of the identifier for like a data structure's purpose, kind of.
I think that it's a natural inclination. The fission folks, I think, have kind of been encouraging. This is borrowing heavily from the UCAN fission approach because it means that the importance of keys are less. The keys can be more ephemeral. So key rotation is less scary of a moment because, and that's the reason I bring up the automation example. It's like I can create a token for A that says, hey, this is my recovery key. And I create a token that says this other key can do everything that key A can do. And that becomes my new backup. And I can use that as a key rotation technique. And the key itself, the token itself really provides a lot of ammunition for whatever that new key does.
Okay. The second question I had for step 5, when pushing, the way we're doing it right now, I guess it's actually more than just step 5, just anywhere where you're merging in logbook data, right? Currently, we're always checking that the signature of the log being transmitted matches like the profile ID in a cryptographic way, right? So basically the access token is a way of just extracting that out. Is that going to be generalized, or do you think access token is going to be like the only way that's able to use that? Like,
no. So that's interesting. It's a really good point. It's not totally abstracting that out, right? The access token only really does set membership. It basically says, and this is part of the object capability model of permissioning, where it just basically says, hey, this is allowed to happen. But the log itself still needs to be verified. So you still need to be able to say, hey, these statements were made by somebody who controls the private key behind branch log A, right? So you do have to check every log. You can't just take it at face value with the public key.
Sorry, I guess what I mean is like, is this customizable from a functionality standpoint? Like,
oh, yeah.
Yes,
right.
Okay.
I cut you off though. What do you have an example in mind so I can make sure that?
I guess what I'm asking is like, is Query Core going to have a authentication scheme that then says whether or not someone can push or pull that is kind of hard coded, or is it possible to like use Query as a library but have some other, someone else wants to use a version that has Facebook Connect, and that's how you decide whether a log can merge or not.
That's a really good point. How pluggable do we make this system?
Yes, yeah, that's a better way to put it. Yeah.
Yeah, and I think that's a really great question for the authentication mechanism. I think there's no reason why we wouldn't. We should definitely do that from the beginning. We should define the authentication spec such that I should say the collaborator membership spec, such that you basically need proof, yep. and the proof could come from many places, and that's a really good point. Yeah,
it's pluggable in a way. It's abstracted and separate from the actual merging. And
and we can say that basically this access token system has the upside of being decentralizable, but that doesn't mean that it's the only game in town. You just need what the collaborator membership function needs to do is wrap a store of some kind and say, for this given thing, please produce for me the set of public keys that are members, that are collaborators on this data set or this subject, right? That's the responsibility that new system really needs to have, if that makes sense. And so we can ask more nuanced questions like, please produce for me the set of collaborators with write access. Please produce for me the set of collaborators with whatever. And that's the other side of object capability definition, where this write access allow write is doing a lot of lifting in this conversation, where we really need to define the different permission semantics and what can and cannot be allowed. And that's really going to be user story centric, right? Like we've encountered folks in the wild who are saying like, yeah, I want to be able to say someone can edit the meta, but not the body, because we have database administrators and we don't, but we also have like people in library sciences who are much more capable of annotating and cataloging stuff. And so that's where, like, ideally we have a system that is sufficiently rich, but ideally has nice high-level abstractions for like right, and which is what I kind of want to be able to say, but the word right means different things to different people.
I'm thinking of a world where there's like a statistician department or something where they just, can change the stats component by running different analysis. And
totally. And we decide what constitutes the median. Yeah.
I mean, having those separate components for data sets, like as part of the model, is a big win there, actually.
Ideally, it maps onto roles. Yeah. And so from the perspective of this discussion, what we really need to make sure we do is we make that system of capability definition and capability and granting definition something that can evolve over time. So we can start really small and say, there's people with write access, and there's people, and everybody who has the data has read access. What we haven't touched on at all here is encryption and the idea of like encrypting data sets at rest and how that will play against this system. To touch on that very briefly, I genuinely think it's another separate subsystem that represents the coordination of encryption keys. They may be backed by the same store under the hood, but what I think we should have is that access token should delegate, and the existence of an access token should delegate whether or not I should transmit the shared secret for this encrypted data set to somebody else. And that's how I think it should be modeled as we move forward. But I will readily admit that that is not a finished thought.
Sounds reasonable so far.
Yeah.
I think that makes sense.
Cool. That was my presentation. Did that make sense so far? Thoughts, concerns? Asmir.
Comments?
Yeah.
So I'll go back to the automation point, but first on Dustin's point about pluggability. I think that's literally the reason for keeping the profile data completely separate from everything else. As the idea, like on our previous discussion, was to, as an example cloud, you use the profile data to prove that you're yourself and basically say, hey, this is me. And that way you can get access to that token that's delegated over there without having the initial private key. And then you can do a hell of a lot of stuff there to work off of that. So I think it's really important that we cut the line between like profile data and identity data and keep it separate. But going back to the automation point, I have a technical concern. And in an example where we have a world with, I don't know, a CI or automation toolkit for, I don't know, building data sets, updating data sets, I don't know, and you mint a new key every time, each of those keys needs to be written back to logbook. And if you're a very heavy user, that can mean a ton of one-off keys being generated into logbook. Do we have a plan on how to handle that? Because like at some point, the user A will have to pull everything, merge everything, and kind of like digest everything. Like, what's our strategy to dealing with like humongous like access token lists?
Awesome.
I think I know the answer to this. One is that we don't need to store the whole, we're not storing the private key, which is larger. We only need to store the public key or even like some hash of it just to prove that it's owned and exists and like, the math works. Also, switching to another key based on elliptic curves can make smaller keys, which would solve a lot of the space problem. But there's probably no avoiding having to see the entire history, I believe. Logbooks deduplication, unfortunately, won't really help here because they're all going to be unique. But yeah, there's at least things we can do to lessen the pain of it. How's that sound?
I mean, it's perfectly fine if we lessen the pain. It's just that like, I don't see a way to reverse any of that. So over time, your data set will become like just bigger and bigger and bigger and bigger, like the whole Git history in there and stuff like that. I mean, one way is to just create a new data set with a fresh history, port over everything. And if it's really, really bothering you and you have a huge, huge log, things get slow. But just wanted to kind of like put a finger to it.
Yeah, we may have to hit compaction at some point. I haven't thought about it. I haven't thought about
cleaning up tombstones and stuff like that. I don't know.
Yeah, and tail compaction in this world is really hard because it's without being lossy in a dangerous way. The couple of things to talk about there. You've really hit the nail on the head, Asmir, where there are practical constraints to some of this. Recent research in the CRDT world has really been trying to solve this answer with compression. And that's, compression doesn't, as Dustin pointed out, compression doesn't really help us much with lots of keys, because lots of keys are intended to create unique values that don't compress very well. That's kind of the whole point. And so I think the answer to that will be the devising some system that in practice actually doesn't mean that you have a key being minted every CI run or a lot. You would just reduce the number of collaborators, of key pair based collaborators in the set. And we would do that actually in a very similar fashion to the way that we do now, where if you define query underscore setup underscore config data, that can actually be a summary of your entire profile information, including your private key pair at the moment. Not so great for a security perspective, but that may be advantageous for two reasons. One is you're not coming up with a really large prime number every time you want to run CI, and you are not bloating your logbook data unnecessarily.
In theory, we could have used the OAuth notion and use some sort of like API key secret to go to cloud, fetch my like latest key, and keep using that until it's like revoked. So you basically CI.
Yeah. Or you could ask for some sort of, we could try to design a system that allows remote signing, right? Where I stream for you a set of bytes and then you sign it. I think that's a horrible idea given the size of data sets that we have or that we're trying to get towards. But it's a point really taken that we could imagine that world as well. I think that I really want to keep us as close as possible to key pair infrastructure. And I think that our ground truth is trying to have keys not move very much and keys be the foundation of coordination. And so for that reason, I'm willing to accept a little bloat in the terms of the number of key collaborators in a branch, but because we're trying to establish portable data, and to make data portable, we need to make a concession somewhere. And I think that's where the concession should probably have. Cool. So I feel like this is the closest we've gotten to like a really clear, a somewhat grokkable definition of how we're just going to pull off multiple key pairs collaborating on the same data set. I think we now have some real projects in front of us. We need a serious set of spec around the auto merge strategy and how it's going to work and how we're actually going to combine these different branches and examination of that. We need to modify our DSRef spec to introduce this notion of identifiers, which we haven't really talked about a little bit, but basically, because there could be multiple users with the same username, we need some new mechanism for disambiguating them. And while we are there, we should formally introduce stuff that Chris has put into a lot of our UI pieces of having short commit references and being able to just like use those at the same time. There's no reason why we're modifying the DSRef spec to not do them both at once. It also is imperative that we be able to directly reference data sets by their historic identifier, skipping data set name resolution entirely. That can be used for performance speed up, but also just as a disambiguation for a lot of this conversation. And we're getting thumbs up party. And then we need to design this store of access token system. I do want to use UCANs for this. So far, I think it's a really nice mechanism, and it has this really nice advantage of bringing us closer to what Fission is doing and allowing this stuff to potentially even be portable across entire open source projects, which I think would be really neat. The real nightmare here is transitioning to elliptic curve keys, which is just going to suck. I'm going to be very real with everybody. This is going to be the like painful work that we have to do to lay out why this work has to happen and why it's probably going to take, I don't know, 5-6 weeks. Currently, we use an encryption scheme called RSA, which is common, used a lot in a lot of places. RSA uses a different mechanism of encryption, which makes the public keys themselves relatively large. And so to go back to the example, the token is token from A to B, which means I need to include the public key of A and the public key of B in that token, or else the token is not useful. And I have to sign the token itself to make the token a claim made by the private key of the owner of that, or of the author of that token. Elliptic curve keys have a much, much, much smaller public key. It's so much smaller that it will drop, like it's orders of magnitude smaller. Don't ask me what the thing is off the top of my head, but it's much smaller, and I think it's 32 bytes for the public key size. Can't remember. But that means that the size of the access token is, we're using RSA keys and lots of tokens. It'll mean that the size of that store will get really large, and that's not good. So we will have to do some work to transition the types of keys that we use to being Edwards curves keys. We want to use the Edwards curve because it's supported, at least in theory, in some of these new web crypto APIs. So query operating in the browser would stay possible if we use the Edwards curve keys, which is important. And when I say query in the browser, I mean like literally like all of the application running in the browser without a server, not query cloud, which obviously will work in the browser right now, but it's backed by a server that has keys. That was a bit of a tangent. Anyways, cool. So we got some projects to do from here. Do we have any major objections to this sort of high-level roadmap? Anything anyone can think of? Oh, no? Cool. So this unlocks a bunch of stuff. When we get this stuff landed, we can do automation, we can do delegated writes, we can do write on cloud, and we have the foundation for encrypted data sets and collaboration in a closed collaboration. All of that comes out of this. So,
B5, the page that you were using to lead the discussion, is that, I saw that you had it on, you were local, but are we planning to publish that or no?
I think it's up right now.
Is it dev.query.io?
Is it? I don't know. No, I think it's query.dev.
Query.dev, right? Okay.
Yeah, and it's at concepts collaboration.
Okay,
yeah, it's
cool.
up right now. Yeah. Yep. Sorry, Dustin, I've just been pushing the master. My bad. But yeah, that's all I had. This is going to take a while to do, but we can now break this down into discrete pieces of work. The next steps are to write more spec. So let's write more spec, and then we'll turn that into working code. Sound good?
Right on.
Dope.
Hugely exciting.
Cool. Yeah, it's fun stuff. Cool. Thank you so much, everybody, for sitting through me blathering for a long time. But looking forward to getting this rocking and rolling.
There will be more.
Cool. Have a lovely Friday, y'all.
All right.
You too.
See you, gang.